Okay, I understand. Your head might be reeling just a little bit from these abstract new properties of continuous curves. So let's sink our teeth into some examples and illustrations. And by the time we're finished with this clip, I think you'll find that the math problems assigned to us are actually not that hard. So I have two examples in this handout. Example number 1 says, Slimy Jaime is living his dream job as a worm scientist. He is studying the lengths of earthworms in Uruguay. Jaime finds that 15% of the worms are less than 40 millimeters long, and 20% of the worms are longer than 70 millimeters. So here is an image of that distribution. I just drew a random curve over top of it because this example doesn't depend on the shape of the curve. It only depends on its being continuous. So again, what we're measuring on the x-axis here is the length of earthworms in millimeters. 15% of the worms are shorter than 40 millimeters. 20% of the worms, this tail, are longer than 70 millimeters. Question 1, or part A, I should say, sub-question A. Would this variable, x, the length of a worm in millimeters, be discrete or continuous? What do you think? The length of worms, would they be discrete or continuous? Well, does the length of a worm, when worms grow, do they stay at one length for some period of time and then just go pop to a longer length and then just pop to another longer length? No, they don't grow like that. That would be discrete. But we know that living things grow continuously. So if a worm started at this length, it would grow continuously, and its length could occupy any point along this continuum. Length is a continuous variable. That's why we've drawn a smooth curve up here as opposed to blocks of rectangles. Sub-question B, if Jaime selects a Uruguayan earthworm at random, what is the probability that x is exactly 62 millimeters? Do you remember this discussion? If I pick any single value on the number line, 62 in this example, the probability would be measured by the area in that so-called rectangle, but there's no rectangle anymore. It's just a little sliver of a line segment. It doesn't have any area. So the probability that the earthworm will be exactly 62 millimeters or any particular length is 0. So that's a meaningless question. Sub-question C, what is the percentile of a worm 40 millimeters long? Okay, well, what do we know about worms 40 millimeters long? We know that 15% of the worms are shorter than that. How does that relate to the definition of percentile? You know what? That is the definition of percentile. The definition of percentile means the percentage of values that are smaller than that one. So therefore, 40 is in fact at the 15th percentile. I'll call it P15. Sub-question D, what is the percentile of a worm 70 millimeters long? Well, what do we know about a worm 70 millimeters long? We know that 20% of all the other worms are longer than that. So this is the worm that cuts off the top 20%. So would that mean that its percentile would be 20? Is it at the 20th percentile? No, because percentile always means area to the left. In fact, do you remember what the term is for the area of this tail? That's not a percentile, that's a p-value. Okay. So if this worm has a p-value of 20%, 20% is to its right. But the question is, what is the percentile? That would mean how much of the curve is to its left. Well, how much area is there under the total curve? 100%. So if we consider all 100% and then we take away this 20%, that would leave us with the 80% to its left. So that makes it the 80th percentile. I'm going to label this point as P80, 80th percentile. Sub-question E, if we select one worm at random, what is the probability that it is between 40 and 70 millimeters long? So in other words, what percentage of the area is in the zone between? And this illustrates that this is the kind of problem that we can actually do with continuous curves. We can measure areas that fall between two values on an interval, okay? By the way, this tail over here is really an interval. It goes from 70 off to infinity. And we can think about this tail as being from, I guess you could say, 0 to 40. Okay, so if we pick one worm, what's the probability that it will land somewhere in this zone in between? And to answer that question, it's really simple, and your intuition is probably right. We just subtract their percentiles. So since we want the worm to fall between the 15th percentile and the 80th percentile, we would just subtract 80 minus 15. And we would find that 65% of the worms are in that zone. Again, I think that's pretty easy to see. If you remember that the area from here all the way to the left is 80, and then if we take away this 15, that would leave us with the 65 in between, wouldn't it? Number 2, the amount of rain in the plains of Maine in May varies uniformly from 3 to 8 inches. That means year to year. Every May can get anywhere from 3 to 8 inches, and that varies uniformly, so all values are equally likely between 3 and 8. What is the probability that next May, Maine plains will receive more than 6 inches of rain? Let's review that uniform distribution one more time. A uniform distribution means flat across the top, every value is equally likely between the minimum value of A and the maximum value of B. And then the height of this bar, the probability density function, has this formula 1 over B minus A, which means, well, B minus A just represents the width of this bar, doesn't it? And then you take that width, you take 1 over that width, and that gives you the height. So that's duplicated on the board. So in this example, the minimum is 3, A becomes 3. The maximum is 8, B becomes 8. 8 minus 3 is 5, right? And that gives you the width of this rectangle. And so therefore, if we plug that in here, it gives us a height of 1/5. That actually makes sense because if you think about this whole rectangle, all of the area, if it has a width of 5, area equals length times, let's call it base times height, right? Area equals base times height for a rectangle. So for this rectangle, the base is its width, 5, and its height is this function, 1/5. Well, what do you know? The area equals 1. That's actually why we use this formula for the height. We want the area to be 1. The process of taking an area like this, which might be indefinite, and kind of choosing a value so that it has a certain area, like 1, is called normalization, confusingly enough. That's different from the normal distribution. So we've normalized this curve so that it has a total area of 1. So it represents total probabilities. Now the question is, what's the probability that next May we will get more than 6 inches of rain? So let's just put 6 here. And again, drawing the regions of interest is always going to be helpful. So we want to, label the axis as clearly as we can, and then label the point of interest more or less to scale. And then we need to shade the region of 6 or more, at least 6. So that would mean 6 and up to the maximum of 8. So we want to find the area of that part, right? What's the probability that next May Maine will get more than 6 inches of rain. So in this case, since this geometry is so simple, we can actually calculate that area. Again, the area of a rectangle is base times height. Now, the base of this zone of interest goes from 6 to 8. That has a base of 2. It's 2 units wide. And multiplied by that height of 1/5, that gives us a probability of 2/5. It's basically just a fancy way of saying that the probability is proportional to this width. If you took half of this width, that would be a 50% probability. If you took all of the width, that would represent 100% probability. In this case, we've basically sliced off 40% of the width, and therefore it would have 40% of the probability. So I kind of like this example. Uniform distributions are actually very rarely encountered in statistics class. I don't think statisticians work with them very much, but it's a good instructional tool because it shows us how the geometry relates to areas. And again, rectangles are so simple that we can actually calculate them. Now, from here on out, though, we're going to be progressing to curves that are curvy, right? So you can imagine how crazy it would be to do this kind of calculation where this height is constantly, continuously changing. In fact, there are only 3 ways to do that. You can either use calculus, a table of lookup values, or a computer. Those are the only 3 ways that you can actually calculate areas under a smooth curve. Calculus, a table of values to look up, or a computer. A traditional statistics class, we traditionally use tables of values. And in fact, there are tables of lookup values in your book, and you're welcome to use them if you like. That's how I usually teach the class. The problem with the tables is that the tables themselves are pretty difficult to learn how to use. So it's one of those issues in the classroom that just is more trouble than it's worth. Students usually struggle so much with the tables that it just obfuscates the lesson. So in this course, I've decided that to give it a try, teaching this with a computer, because StatCrunch does these calculations for us. So that's what we're going to be doing next. We'll take a look at these curves like the normal curve, and we'll learn how to use StatCrunch to calculate the areas. So we won't have to use calculus or formulas or even lookup tables. You kids have got it so easy these days. All right, let's move on.